All right. Hello, guys. How are you? Hope you're doing well. This is Leonardo Cap, and welcome to my channel. And today we are going to do another video on coordinate geometry. So it is a multivariable calculus 1 and the lecture 1. Previously, we have talked about the syllabus, and now we're going to start with our first lecture, which I'm going to discuss on lecture 1 coordinate geometry. So let's get started. So yes guys, as promised, today I'm going to start with the coordinate geometry, and this coordinate geometry first we are going to understand little more concept on how to deal with how do we measure distances on the 3D space. So you first understand the coordinate system. The coordinate system is composed of the three axes which are perpendicular to each other. We can namely use we nomenclature as x, y, and z. And these x-axis, y-axis, and z-axis are basically perpendicular to each other. Now, if you take three lines and if they are perpendicular to each other, then they will always pass through only single point. And if such thing happens, then we call it as 3D space. So in the 3D space, you can have maximum only three lines, which is going to pass through just single point if they are perpendicular to each other. So this is one way of thinking. Another way of understanding the 3D space is that you can move around like left, right, back and forth, and up and down. So this having the degree of freedom in three directions or is called the 3D space. On the other hand, you have the 2D space. In the 2D space, only two lines are perpendicular to each other passing through a single point. Only two lines are possible. Or you can just say that either you can move left and right and up and down, or back and forth and left and right. So any combination you can take. This is called, you have x, y, and we are calling it a plane. So when you have a two dimension, it will make something kind of a plane. So like this or like that and so on. The example of 3D is you can consider square and all these things, all right, where you have just only the length as well as the width. There is no any height, so you cannot just come and back and forth. So if you are seeing the screen, you cannot, nothing can come outside the screen and go inside the screen. So everything happens in the surface. All right, so you can just basically see that whenever you have xyz, you have some kind of plane, and this plane has something kind of surface. So a surface having a two-dimensional kind of structure. On the other hand, if any object is in three-dimensional space, then you have surface. Let us say you can visualize a very simple example is called sphere. In a sphere, you have the outer surface, and also you have volume. On the other hand, in the 2D surface, you will not get any kind of volume. So volume is zero, means there is no any volume, but surface is there. So surface is finite, surface is not zero. Over here, volume is also finite, surface is also finite, as well as it has also line elements or length. Now, when we are considering the one dimension, then in one dimension, either you can move in particular direction, all right, either in either in left, right, or up and down, or back and forth. So a point is always a point there. Obviously, a point is also, you can just take a point and you can have the coordinates over here. You have the points coordinate over here, but in 1D you will require just only a one parameter to localize it. All right, let us say you can just have only x in order to locate this point. Over here, in order to locate the point, you require x comma y. Over here, you require x comma y comma z. So these are some things, or some basic stuff of the coordinate system. On the other hand, if you have any kind of point over here, you can have point obviously, and you will have only line. So this line does not have any surface, and neither it will have any volume. So the surface is also zero, there is no surface, as well as volume is also zero. So this is basic thing how we can distinguish one dimension, two dimension, as well as the three dimension thing. In three dimension, you will get volume as well as surface. You will require three parameters to locate any object. On the other hand, if you are in 2D, then you must have only two degrees of freedom, or two ways you can move around. You require only two parameters to locate any object, and you will not have any volume. You may have surfaces, and everything is making some kind of a plane. On the other hand, if you are in 1D, that requires only one parameter to locate, as well as it will exist as a line. There is no any surface, no volume. So this is a basic property of the coordinate system. Now the one thing is that how we locate it. Now in one dimension you have already understood that, okay, just write down 5 centimeter is there, as you have already worked with your ruler. So let us see your scaling part. All right, ruler scaler at 0 1 2, it is, so this is appearing as a line. So this is just one dimension. So if you want to measure from here to here, you can just put it your scale over there, and you can just report it 5 centimeter. But on the other hand, if you are in 2D space, what you actually do is that, let us say you have any point in X and Y geometry, then you can just say that, okay, I have coordinate system, I have, location of this point, let us say X1, Y1, or you may say that X and Y, never mind. And whenever you try to find the distance, you have to first define the perpendicular distance from here and to from here. So once your perpendicular distance is already defined, then you can just say that, okay, I will take distance which is going from origin to a line which is going from origin to that point is basically given by r. And so this hypotenuse of this right angle triangle will give you the distance of this point from origin, or of this point in this plane. So the distance can be figured out by using over here x minus 0 square plus y minus 0 whole square. Now in terms of vector, let us say I am name it OP. In terms of vector, I can also find the distance. How we can find the distance? Because when we have drawn this P, then you can see over here that it is actually something take some distance. It is taking in X, so I can just write it as, let us say, Q. So I have this OQ vector, and when I have arrived this OQ vector, I have drawn a perpendicular which is parallel to this y-axis, then we are actually going from Q to P. So in order to reach this point, you have to first go travel from O to P and then Q to P. And then from the triangle's vector law, you can just reach from O to R. So how we can reach this point? O to Q vector and then Q to P vector. And similarly, I can just reach there O to P vector. Now we can consider that it is x1, and from here to here it is y1 because it is parallel to this one. Everything is parallel. So I can just write over here x1 vector plus, I don't know what is the, oh sorry, yeah, I know y1 vector is equal to r1 vector. So this is we can write it down because as a vectorial quantity. So this is the vector quantity of this point because we are talking about a 2D plane. And in order to find the distance, what I can just say that I can just take in order to find the magnitude, what we can call the distance or position, the magnitude of position vector is just writing x1 magnitude square plus y1 magnitude square. Or in terms of the coordinate, what you can just write in mathematically, that is square root x minus 0 whole square plus y minus 0 whole square. So these two definitions, either you think in terms of vector or in the things in terms of coordinate geometry, they are basically an equivalent thing. All right, so we have to first properly define it, how much of this quantity in x and y, and then we can just figure out what is x1 and y1. So this is the same thing as x and y, x1 and y1. All right, and the origin is already set in 0 0. Now consider that you have again x and y, but the line is not at all, there is some light which is finite over here. So consider you have the PQ line. Then how will you measure the distance? First of all, you have to locate what is the coordinate of this from origin. Okay, so that is the meaning of coordinate system. We are drawing a coordinate system in order to locate the points in space. So if you have line, then there is an end point of this line. So let us say first we denote P as considered to be x1 and y1, and then we can write Q, which is, let us say, your x2 y2. So I want to find what is PQ, P from Q. So from the vector point, what you can see that I am going from OP to, then I am going to PQ. So OP to PQ, and then I can directly jump to OQ. This is the vector way to doing it. Now OP vector could be anything. It like, so I can just write here PQ vector is equal to OQ vector minus OP vector. Now, what is this OQ vector? OQ vector is just showing you the position vector, because again, this is this is a line. Sorry, this is a line. OQ is basically a line. So this line is showing you the position vector. How we can determine the position? Just like x1 and y1. What was x1, y1? X1 was uh, the distance between two things. So here 0 minus x1 is basically x1, 0 minus y1 is y1. So over here what we can just show is that x2, 0 minus x2 is x2. So I can just simply write over here that x2 comma y2 minus x1 comma y1. So what does it mean? It means that when I'm writing x2, means that it's showing you the x coordinate. Y2 means it's just showing you the y coordinate. Over here also x coordinate and y coordinate. And we understand perfectly well that x is actually subtracting with x and y is subtracting with y. So I can just, in terms of, I can write over here x1, x2 minus x1 and y2 minus y. So basically getting this coordinate is basically telling you what is the PQ vector or position vector. So whenever you are writing, let us say, any vector in 2 dimension, it has certain components or certain magnitude, and then you are writing it, let us say, x hat in the x direction, certain thing in y direction. Or in similarly, I can just express this thing as a, in brackets, ax and ay. So this is basically a same thing. So over here you are just getting x2 minus x1, y2 minus y. Now, if you don't want the vector representation, we can just directly do it by, saying that, all right, we have the coordinate. So one coordinate is P, one coordinate is Q. This coordinate is, we can find by using this origin and all these things, x1, y1, and Q can be written as x2, y2. Then the distance between them is going to be x2 minus x1 whole square, y2 minus y1 whole square. Now same thing also apply over here. I can just write PQ, and then there is a magnitude x2 minus x1 whole square plus y2 minus y1 whole square. I hope this is clear to you. So whenever we try to find out any distance, any position in a 2 dimensional space, then we have to first locate these endpoints. These endpoints will give you the coordinates, and these coordinates are telling you that how much it's in x, how much it's in y. So once you have located it, then you can use the triangle rule of the vector, and then you can easily find out this guy. So we have done the two ways. One way is using the coordinate geometry. We understand how the coordinate geometry works. You have the two coordinates and you can just subtract the same coordinates in the same orientation, like over here we have done. Or you will have, one can always ask that how do you know you have to subtract it. Over here we had the explanation. You can just use the vector coordinate system or the vector representation, and from there you will understand that whose coordinate is this one. So whenever you have to find the position vector, you must require some magnitude as well as the direction. And in order to do it, you can just divide it into the components. So whenever we have something, we are always trying to divide it into how much in x and how much in y. Once you have figured out that how much in x, then you can just subtract it from the origin. So the requirement of coordinate system is that you understand that there is a origin, and from that origin you can have only two, at most two lines which is basically perpendicular to each other. So now you have fixed your origin, and now you want to measure some certain points, then you can just take the distance from that origin to certain points. Now you can just do it by taking some components in perpendicular to x and perpendicular to y. All right, and then you got x and y. Once you have done this x and y, then you can either use coordinate system, coordinate geometry, or you can use the vector, and then you will have the distance. Now same thing I'm going to do with the 3D case. So I hope I'm not going very fast, but if you find any difficulty understanding this concept, then please write it in the comment box, and we will have again extensive discussion on these things. Now let us try about 3 dimension. Now in 3 dimension, we mainly we are not using x over here just for a traditional way, x, y, and z. Now in x and y, let us say we have anything which is basically in over here. Now you do not think it as something in y and z plane. It is some in space. All right, just like let us say you can take a ball and you can just mark some point there. So you can think of it that from the center of the ball x, y, z is passing, and then there is something in the space. So this is how it is. So first of all, we have to take, okay, so this is in some kind of z, all right. So what we can do is that first of all, we can have the same thing in x and y. From here, this distance and this distance are basically same. So this point and this, we are taking a projection. Let us say you are just using a mirror, or you can just say that, okay, I can just take this point in x and y plane. Now what we can do, I can just make a perpendicular from y, because this is my origin, and perpendicular from x. So I have over here what we have done already, x and y. So once we have x and y, then we can go to some z. So this is how, and whenever we have to find the distance from the origin, then we can just write over here r vector, or the position vector, or distance, magnitude of r vector is distance. So when this point was in x and y, then you can just coordinate it as x1, y1, or xy, whatever, with z is equal to 0. But whenever you are here, how much z you have traveled, then you can have the coordinate as x1, y1, and z1. So first of all, we are going to just find out what is the distance in x and y plane by using the rho. So rho is becoming x square, x1 square, y1 square plus 0, because there is nothing like 0. You can just say that, okay, it is 0 comma 0 comma 0. So this is the rho. Now once you have done this one, then I'm going to go over here. So how the r will look like, r becomes look like as how much is in, so rho. So you can see over here that it is making certain angle, right? So this is basically perpendicular over here, and this is just there. So I can just find out r square like this. So from, we are going from here to here and then here, right? So you can see that O, let us say I'm naming it P and Q. So I am basically going to, in order to measure OQ, I am first going to OP vector and then PQ vector, and then I will just arrive at OQ vector, all right. Now OP vector is basically your row vector, and the PQ vector, which is I don't know, and therefore we have OQ vector. Now this OQ vector is given as R vector, all right. So in order to find this R, the magnitude of this R vector, I can just simply write here magnitude of row vector and the magnitude of PQ vector. Understood? So once you know what is your Q square, so if I am going to square it, then I will get this one. So I will have x1 square, y1 square plus 0 square. Now PQ, what is PQ? The PQ is given as just only z, because it is how much you are actually progressing towards z. So this will just having z square. So what is the distance now you have come? X1 square plus y1 square plus z square. So either it is z1 and z, they are basically the same. So the distance in 3D has now become x square plus y square plus z square. All right. Another example we can use is, like, let us say that I have certain PQ length over here, PQ. So I know how much we can locate it using x1, y1, z1. So let us say it is x1, y1, comma z1, and over here it is x2, y2, comma z2. So I can measure the distance between them by using, let us say it is RP, it's RQ, all right. So from here to here, you will get RQ minus RP. Therefore, I can just write the distance. So let us say PQ as a distance is equal to x2 minus x1 whole square, y2 minus y1 whole square, and z2 minus z1 whole square. So this is how we are going to find any distance in three-dimensional geometry. So you understood the few points, that how we are basically going from 1D to 2D and 3D. So once you understand how to go from 1D, because 1D is a very simplest case, and you have understood how to deal with 2D case, now 2D, and now so from 2D to going 2D to 3D is basically very easier one. You don't have to do anything. Now, similarly, we are in three-dimensional space. But if you are, heard of Einstein's theory, you understand that our universe is made up of the four-dimensional geometry, which we cannot visualize. We can understand that how we can move back and forth, up and down, and right and left. But we don't know how to move in the fourth dimension. We are not a four-dimensional being, but the universe is a four-dimensional being, four-dimensional object, you can say that. or entity. So we are not certain entity which have the liberty to move in the time dimension. All right, so he has said that okay, they have in our universe there are three spatial dimension and one is called time dimension. Now, for an example, if I want to move from 3D to 4D, how are we gonna move it? Because visualizing a distance or visualizing an object in 3D is going to be very hard. So in this video, we are going to basically going on those things that how we can deal with more spaces. Obviously we are not going to deal with general relativity over here, but I'm just giving you that okay, what type of mathematical language have to deal with in order to do that. But before that, I have something in mind. I am something in mind that okay, once we have understand these things, one important thing you can say that how to represent something in three dimensional form. Consider I am taking an example. Let us say I have over here x 2D space. In 2D we can have certain point. Let us say somebody has given a coordinate x1 and then it is 0, y is 0, all right. So this is x1. So in order to plot it everything in a 2D, then y will become, it will be simply parallel to y axis, because y becomes 0. So there is nothing wrong, there is nothing. So see, what you have to do is that it is simply extending parallel to y axis. Now it will be very interesting to see, it is called representation, how we're gonna see, because we understand that in 1D you have line, but in 2D you will have plane. So this point has now become a kind of line in x and y. Now you can have x is equal to y, right? So x is equal to y, you have this straight line relation like this. So obviously in 2D it is x is equal to y, there is no any z involvement. Now for an example, I want to visualize this x is equal to y in three-dimensional geometry. So consider over here I have x, and this is not, sorry, this is z, this is z axis, this is y axis, and this is x axis. And now I have to understand how this x is equal to y look like. So x is equal to y will have something over here and something like this, right? So a line which is passing through origin with 45 degree of angle from x axis, right? Now in order to see that x is equal to y in a three dimension we have the volume and also surface. So the thing is that in 3D you will have surface, but this line does not have surface. How are we going to make it surface? So once you do not have given anything xy, and the coordinate would become 0, then what you can just do is that you can just make a plane by parallel with z and minus z axis. All right, so this is how it will look like. At each z is equal to 0, at each point it is basically making an x is equal to y plane. All right, so this is a kind of plane which is whose origin is always x, z is equal to 0. So this is kind of stuff that you have to draw, that how we can see it. Similarly, we can have a circle. For an example, consider I got a circle, x square plus y square is equal to 4. So in 2D it will be simply circle, but what happens in 4D? Sorry, in 3D. In 3D I can have, this is x and y, so this is circle, but z is not there, so z is equal to 0. So you have to make a concentric circle. So if you have a concentric circle, then how it is look like? It will look like a cylinder. So a cylinder whose radius, so this is radius, so radius is basically radius square, x square plus y square is equal to r square. So r is basically 2. So from each z it is basically 2. All right, so this is how a circle will look like in three-dimensional space. In 3 dimensions it is now just become a kind of a cylinder, right? Now if you do not, if you have something like x square plus y square and the finite z is equal to, let us say, 25, then we have r over here is 5. All right, r square. So now since x and y and z everything is there, it means that the distance from x, y and z is always be 5. So this is 5. So once you have this one, you can think of it as a sphere, because in 2D if you have x square plus y square and r is fixed from the origin, then it is just like a circle. But when you are in 3D, then everything is becoming constrained by some kind of radius, then it is becoming a surface. So x square plus y square plus z square is equal to 25. So the radius was become uh, the the radius of the sphere. All right, so once we have done with this one, now we are going to understand a few important things. So what we have now we studied something very special kind of. The special means that we have studied three-dimensional space where these are basically perpendicular to each other. Now we can have some spaces where this x, y, z may not be perpendicular. We may have some spaces where x, y, z, maybe k, l, m, n. So we can have many dimensions. One cannot just say that we are limited with n is equal to 3 dimensions. We may have 4 dimensions, 5 dimensions, 6 dimensions. Since our understanding has not reached there, so we don't know anything about it. But people have already constructed some theory on more than 5 dimensions. For example, n is equal to 11 dimension is a theory for string theory to work, right? So from the string theory approach, it is given that our universe is made up of 11 dimension, and this 11 dimension is required in order to marriage between quantum mechanics as well as the gravity. All right, but so far we are not going to do that one. But that is the obvious question, that okay, we cannot have just only x and y and z. We can have more dimensions, x, y, z. Now once we are entering more than 3 dimensions, then the geometric way of thinking has now end up, because you cannot just simply say that okay, how the cube will look like in 4 dimensions, how something will look like in some dimension. As you have seen, no, that a circle will look like a cylinder. If you have no z is not equal to 0, then everything becomes a sphere. So how a sphere will look like in a 4 dimension, 5 dimension, 11 dimension? So we have to lose the meaning of geometric meaning of certain things, and we have to use some algebraic meaning. And because of that, we have to use some mathematical reasoning, and this mathematical reasoning comes from certain algebraic definitions, and we have to use a terminology, mathematical terminology called topology. All right, so that is what things become very interesting and amazing when you are basically going from n is equal to 3 to 4. Now, obviously, you can have more dimensions with mutually perpendicular to each other, maybe 4, 5, and 6. But they will be not mutually perpendicular, because we have already seen that in x perpendicular to y perpendicular to z. So whenever you have x perpendicular to y perpendicular to z, then we can just simply say that these are Euclidean space. Now, what about non-Euclidean space? Non-Euclidean space does not necessarily to be perpendicular to the perpendicular, does not require it. For an example, the sphere of surface. The sphere of surface is not kind of perpendicular or non-Euclidean, because if you had just plotting a triangle over here, the sum of the internal angles is 180 degree. But if you are plotting a triangle in a sphere, it will look like this. So the sum of internal angle will be greater than 180 degree, or maybe is less than 180 degree. So when we are talking about some spaces more than 3 dimensions, or something they are not perpendicular to each other, and a lot of things can happen, then we are entering at the algebraic properties of certain of those configurations, and we are going to label things as the numbers, because when we are talking about xyz, xyz are collection of numbers. All right, and this collection of numbers we are going to call it tuples. All right, so in n dimension we have n tuples, and in n tuples we are going to label it as x1 y, x1 x2 x3 x4 and xn. Why we are adopting this strategy? We are adopting this strategy is because we don't like so many alphabets, because again, representing n number of dimensions, we are going to run out with all these things. So x1 x2 x3 are the real quantities, they have to be the real quantity. All right, and but so this is called for real quantity, but they are part of the real space, and this real space of we can just write it as r to the power n. All right, so this n is shows the number of dimension, number of tuples. So for n is equal to 1 we have 1 dimension, n is equal to 2 or the plane, n is equal to 3 is the 3 dimension, 4 is again 4 dimension, and so on and so forth for n dimensions. All right, so this n has to be real quantity. All right, so in most of the lecture we are going to restrict ourselves to n is equal to 3, but when we will do the general relativity and maybe some more abstract space, then we are going to talk about n is greater than 3. So we are going to talk about n is equal to 4 and so on. All right. So the thing, that definition that you have to understand is that x1, x2, x3, comma xn, these are, we can so call is the tuples, and these tuples are collection of real numbers and so on. All right. So you understand n is equal to 1 means that 1-dimensional space, 2-dimensional space, 3-dimensional space, and 4-dimensional space. So for an example, just giving you just an idea how this R4 look like. So Einstein has so first of all, the Minkowski was there, who said that, all right, you can always have R4, and in R4 t is perpendicular to x, is perpendicular to y, perpendicular to z. So he said that there is another coordinate which is called the time coordinate, and this time coordinate is going to be perpendicular on three spatial coordinates which are also again perpendicular to each other: x perpendicular to y, perpendicular to z. All right, because we are not restricting ourselves to 3 dimensions. So there are four lines which can be perpendicular to each other, but we cannot visualize that one. So similarly, so this is called R4. Now we can measure a distance again the same way. We cannot draw it 4 dimensions. We can say that, okay, this one would be t1, x1, y1 or z1, or over here t2, x2, y2, and z2. And we are just simply say that, okay, distance or the position where the magnitude of the distance would become t1 minus t2 whole square, x1 minus x2 whole square, y1 minus y2 whole square, and similarly z2 minus z1 whole square. Although I am labeling it as a time dimensions, I'm just using the name, but the thing is that I am not giving any physical meaning over here that this is have to be time and so, because again, if you will go there, then certain things will be changed, and it is not looking like that one. It has some physical reasons, but I'm not going to deal with it. So the thing is that we have to think of in an algebraic sense that how we can proceed from 3 dimensions to 4 dimensions. So it is a very specific kind of configurations where we can call it as a Minkowski configurations, where time is represented as dimensions and it has certain geometry over there. But the thing is that we can measure the distance and all these things we can do, but we do not visualize it. We do not say that, okay, how the geometry will look like, but we will be interested in more of it, or more of its geometry. All right. When you're talking about the space, all right, so space is a collection of points, all right, and these points are going to be real. So when we are talking about space, space means collection of points, and we have to represent it. When we are going to talk about some collection of real number, collection of complex numbers, and all these things, then we are basically entering into set. Set is always give you some collection of things. There could be empty set, there could be some set, and there could be union of set. Let us say you have some union set. You may have some intersection of sets. All right, that something is there, something is there. Let us say 2 and 4 and 4 and 3, the intersection would become just only 4. So these sets is containing some kind of collections, or these are called elements. All right. So let us say you have Rn. Rn is big Rn dimension. Everything is happening inside this Rn. All right. You can just say that, okay, R3 belong to Rn, or R3 subset of Rn. All right. But R3, I cannot just say that Rn is subset of R3. Can I say no? R3 has a lower dimension than Rn. All right. I can just say that, some excluding, let us say there are R1, R2, R3. Let us say RC, which is called the complement of, RC of 3. Let us say there is some kind of a space, Rn, and we have, let us say, collection of something. Consider to be, RC3 is basically representing on R4, R5, and R5. They're also, subset of Rn. Understood? So let us consider that I have a certain point on Rn, a point P on Rn belongs to, let us say, Rn, right? Now we can obviously define some neighborhood of this point, that is P. For an example, in one dimension, the neighborhood would be extreme. Let us say P is at the center, then we have at minus R this one and plus R this one. So I can just say that P minus R and P plus R, there are two endpoints. All right. Now in 2 dimensions, it will become just like that, x and y. So when you understand, let us say this is point P, so it has now becoming a circle. So I can just write it over here that the radius x square plus y square is equal to r square. So if this condition is satisfied, then all the points is on the boundary. All right. So this is going to be on the boundary. On the other hand, if I'm saying that x square plus y square is less than r or less than r square, then we can say that we are talking about the interior of this point. Now, if we say that x square plus y square is greater than r, then we are basically talking about this space. Let us say this is called, this is SC space, and this space the interior of this one S. So any point which is any point, let us say some point that is q. So if p minus q, we can just say, consider to be magnitude, and let us say this is the distance of the neighborhood, is less than r, then we can just say that whatever this set would be the neighborhood of p. So I can just consider that br of some point p is called the neighborhood of this one when some q belongs to Rn in such a way that distance, or I can just write over here that p minus q is such that p minus q, the distance between p and q, has to be less than the radius of this one. Now it could be 4 dimension, 5 dimension, and so on. So consider I have a point in Rn space and I want to define its neighborhood, and how the neighborhood will look like. So I can obviously take some point and I am just going to measure a distance. So if this measurement of the distance having some geometry, if I'm talking about the Rn space, there could be some kind of geometry of it. Okay, there is some kind of boundary of it. All right. So if any point is inside the boundary, then we can call it as a set is called open set. All right. That okay, it is not in the boundary, it is basically inside a boundary. So anything, let us say I'm just saying that okay, how we can just, let us say this is a line. If you are not, if you are excluding these points, then we can just say that it is an open set. All right. So similarly, you have the 2D and the 3D. So in open set, when we are excluding the boundary, so in 1D, it is called as open. All right. In 2D, it's open disk, because again, it has all the collection of points inside this boundary. So we can just call it open disk. And 3D, or in 3D, we can just call it as an open. In 4D, it will become two open balls or two open ball and so on. So something is different. The name will go different. So if you are excluding the boundary, then you are entering as an open set. Open set does not include boundary. So over here, it is not an open set. It is becoming closed set. Over here, it's an open set. Now it is basically exterior. So if I am talking about that S is such that, or S is basically the neighborhood of point P, then S can be open. So S is an interior point. S can be open and interior point. X can be exterior point. If S is exterior point, then we can have to label it as SC, because SC is there. Any point which is not in the set S is becoming SC. This is called exterior point. And if something is on boundary, then we can just say that something is in boundary. So the point which are just simply on the boundary. All right. So the name goes that if you have open set, then in 1 dimension it is just open, in 2 dimension it is becoming open disk, and 3 dimension it is becoming open ball, and similarly in 4D 2 open balls, 3 open balls, and balls, and so on and so forth. So I hope this is making some sense. I'm giving you some idea of set. I'm giving you some idea of how to measure the distance in 2D, 1D. So this lecture is basically surfacing, scratching the something which is going to come, a very important things that we're going to discuss. So I hope that this lecture give you an insight which was missing maybe, or we knew, or you maybe knew this concept and so on, but revising these concepts are very important. And when we are going to do more of the things, then I'm going to again use the set and all these things, what we call the interior set, open set, and all these things. Then from this lecture, on the basis of this lecture, I'm going to use the terminology, tuples, what are the tuples, topology, and all these things. So I hope this lecture may give some meaning to you, may some increase your knowledge and all these things. If this so, then please subscribe my channel, hit the like button, and also hit the notification bell, because whenever my video will arrive, you will get the notification and you can as soon as possible watch and share. Yes, Leonardo Cap signing out.